Hello again, Physics 20s. In today's lesson, we are going to talk about a fundamental wave property that is referred to as interference. And then we're also going to start to shift from looking at wave motion in one dimension to a two-dimensional plane. Learning outcomes are to explain qualitatively the conditions for constructive and destructive interference of waves. 2, define the terms wavefront and ray as they apply to describing transverse and longitudinal waves. And 3, explain qualitatively the phenomenon of reflection as exhibited by mechanical waves. The learning outcome 3 has been stated before, but this time we're going to apply to a two-dimensional plane compared to just the one-dimensional line we looked at before with a string, like a wave pulse on a string. Okay, so interference, which is a fundamental wave property. When I say it's a fundamental wave property, it is something that only a wave can actually exhibit. Interference occurs when two waves that are moving in opposite directions meet. When they meet, they actually just pass through one another. Now, this is very different in comparison to how regular matter behaves. So for example, for regular matter, if I took like two marbles, say we had like marble 1 moving towards the right, and marble 2 moving towards the left. When they meet, there's going to be a collision. And then what would happen is after they collide, assuming they have like the same mass and same speed, then marble 1 would just get reflected back towards the left. And marble 2 would get reflected back towards the right. So waves, when they actually meet, pass through each other. They don't hit and reflect. What they do is superimpose. Superimpose means, in a sense, their amplitudes add together. And then we get a larger or a smaller wave depending on the situation. And we'll look at the two different kinds of interference right now. Okay, so yeah, when they superimpose and interfere, it creates a temporary waveform that is the sum of the two waves. And I say the sum of the two waves, I'm looking specifically at the amplitude of the two waves. So we'll start off with constructive interference. Constructive interference occurs when two waves meet in phase. So when they meet in phase, it means that crest meets crest or trough meets trough. When they meet in phase, the waves actually give you a larger waveform. So let's look at an illustration of this. So in this picture, I have two positive wave pulses. I have wave pulse 1 that's moving towards the right and wave pulse 2 that's moving towards the left. When they meet, they actually combine together to give you kind of like a jumbo wave, a much larger waveform. They superimpose. And again, superimpose means they create a temporary wave that's a sum of the two waves, specifically of their amplitudes. But then the weird thing is after they actually hit, they just keep moving as if nothing ever occurred. So wave 1 was initially moving towards the right. After they interfere, that pulse just keeps moving towards the right. Wave 2 is moving towards the left, and after they interfere and superimpose, it continues to move towards the left. And again, this is only something that a wave could actually do. Again, because regular matter, when it would meet, would just reflect and collide. It's not like when the two marbles meet for a brief instant, you get like a jumbo marble that's like marbles 1 and 2 combined, and then they split apart and go their separate ways. So normal objects, normal matter like particles, cannot exhibit the interference property. So it is fundamental to waves only. So yeah, obviously this does not happen. Destructive interference occurs when waves meet out of phase. So when waves meet out of phase, it means the crest of one wave meets the trough of another one. And in this case, the superimposed wave cancels the amplitude out a little bit. So whatever your amplitude of your two waves are initially, it gets diminished a little bit or it gets completely eliminated. So in this example, I have wave pulse 1 as a negative wave pulse, and that's going to meet up with wave pulse 2, which is a positive one. And again, these two guys are out of phase because you're going to have a crest meet a trough. Now, what happens this time is when they meet, because the amplitude of pulse 1 is negative, because it's a negative wave pulse, and pulse 2 is a positive one, if you add the two amplitudes together, they actually cancel off to give you nothing. So it's like if you thought of this in terms of like generating wave pulses on a string, it would be like the string is just briefly at rest for a moment. There's no pulse at all. But then afterwards, they just continue moving as if nothing happened. So 1 keeps moving towards the right, and then 2 keeps moving towards the left. Now we're going to shift gears to looking at wave motion in 2 dimensions, as opposed to a straight line, now a 2-dimensional plane. And we're going to distinguish between 2 words, or 2 phrases or words, a wave front and a wave ray. So a wave front, think of it like this. You're a bird and you're looking over like a body of water, and what you're observing is like little ripples. Maybe someone dropped like maybe they dropped like a log into the water here. Just plopped a log or I don't know, some kind of object like straight down, and it's going to generate a bunch of ripples. So we'll focus on the ripples going in one direction towards the right. So the log that dropped is the wave source. Okay, so the ripples I would see, those are what we call wave fronts. In terms of what the ripples actually are, again, we're having the wave energy propagate towards the right here. Those little ripples you see would represent the crests. So in a wavefront diagram, if you're looking at it from a bird's eye view perspective of the water, you're only drawing the thing that's closest to your perspective. So the part of the wave closest to your perspective is the uppermost portion of the wave, which is the crests of the wave. Directly in between them, although we don't draw them, would be the troughs. So wavefronts just represent the crests when we're actually looking at a wavefront diagram. A wave ray diagram, a little bit easier to draw, just shows the direction of the wave propagation. And again, the direction of the wave propagation is telling me what direction the energy is moving as a result of the individual particle vibrations. So a wave ray diagram would just be an arrow that points in the direction the wave energy is propagating. No need to draw the wave fronts in this type of diagram. Now let's come back to reflection, although this time, again, we're going to look at it in the perspective of a 2-dimensional plane. So let's start off by, again, let's pretend that we're looking at this scenario from the perspective of a bird. So I have some kind of reflecting surface at the bottom here. So this could just be like a wall, solid wall. Okay, and what we're going to do is there's some kind of source of a wave, and the energy is going to start to propagate down and towards the right, towards the reflecting surface. It's a lot easier if we just draw the wave ray in comparison to the wave fronts. And one connection, just a note, between the wave ray and the wave fronts is that they're perpendicular. So these crests right here would be perpendicular to the direction that the wave energy is propagating. Okay, so we're just going to focus on the wave energy that's going to hit this wall. The ray of light that's going to, not ray of light, the ray, which represents the direction of the energy transfer, the one that is going to approach the reflecting surface, is what we're going to refer to as being the incident ray. When it hits this wall, it's going to, of course, reflect. So we'll draw a couple of these wave fronts reflecting away, but again, it's a lot easier just to construct the wave rays compared to the wave fronts. So my wave rays, again, would be perpendicular to the wavefront. That's supposed to be a little square symbol indicating perpendicular. And the ray that moves away from the surface is what we call the reflected ray because it's hit the surface and now it's bouncing away. At the point of contact of this wave ray with the surface, if we draw a line at this point of contact that is perpendicular to the reflecting surface, we call that the normal line. And I think in mathematics, whenever we make reference to something that's a normal, it is making reference to a perpendicular quantity. So a normal line is perpendicular to the reflecting surface at the point of contact where we're looking at the wave ray. Theta 1 is the angle from the normal line to the incident ray. We call that the angle of incidence. Theta 2 is the angle from the normal line to the reflected ray. We call that the angle of reflection. Now, I suspect you're familiar with the law of reflection. What the law of reflection tells you is that the angle of incidence is always equal to the angle of reflection. So in this diagram, theta 1 would be equal to theta 2. The important thing to note, though, is that theta 1 and theta 2 are always measured relative to the normal line. So yeah, I could draw a couple of other angles on this picture. Like I could call this one theta 3, and I could call this one theta 4. And it is true, theta 3 is equal to theta 4. However, we don't call theta 3 the angle of incidence. We don't call theta 4 the angle of reflection. The angle of incidence and reflection are always measured relative to a normal line. And if you're wondering what the reason is for that, well, it's not a big deal in this situation because our reflecting surface is a planar surface. It's like a nice flat surface. But this would be more of a problem if our surface was curved. Like if our surface was curved, kind of like this, then you'd have a problem measuring the angle here, because like an angle really needs to be measured between one straight line and another one, not between a straight line and a curve. Even if we did have a curve, though, we could still construct a normal line, and we could always measure that angle of incidence and reflection relative to it. So just be very, very cautious that whenever you're being asked to either measure an angle of incidence or reflection, it is relative to that normal line and not to the surface. A very, very easy mistake to make, but also like a really kind of like foolish one if you don't know the terminology. Okay, let's get into a couple of examples. One of them will be dealing with interference, and the other one will be dealing with interference, and one will be dealing with 2D reflection. Okay, so what I have is it's showing two waves that are passing through each other at a given point. And what I want to do is I want to graph the superimposed waves. The superimposed wave can be constructed by just putting these two different waves together, their amplitudes. Okay, so we're going to use a table of values to help out with this, just because like the waves I've drawn right here are a little bit complicated. So let's see what we've got. So what we're going to do is let's call the wave that is like bolded, a bolded like solid type line. We're going to call that one Y1, and we'll call the dashed one Y2. And what we're going to do is we're going to measure the amplitude of each of those waves at all these different points. And then we're going to figure out what the superposition is by adding them together. Okay, so when x is 0, y1, the solid one, starts at 0. When x is 0, y2, well, it's up at 4. How about at 1.5? So 1.5 would be about right here. Okay, at 1.5, it looks like the solid line is probably somewhere around 1.5 centimeters in height. And the dashed line looks like it's at about maybe like 3.25, a little bit above 3. Okay, at 7.5, so 7.5 would be here's 5, 6, 7. 7.5 is right here. So that's where we're going to have a slope change in both these graphs. Okay, so y1 would be up at 5, and y2 would be down at -4. Okay, how about a 13.5? So 10, 11, 12, 13. 13.5 would be about right here. So let's try to figure out what these amplitudes are, or not amplitudes, what the wave height is at those positions. Okay, so the solid line looks like it's about 1.5 again. And the dashed one looks like it's sitting at maybe about 3.25 again, or 3. We don't have to be perfectly measured. Let's just kind of get it in the ballpark. Okay, 17 and a half. So here's 15, 16, 17. So 17 and a half would be located here. Okay, so y1 is now below the x-axis. That looks like it's about maybe, I want to say negative 2.5 maybe. And y2 would be at, looks like it's about 2. 22 and a half, so we'd have 20, 21, 22, 22 and a half is here. So again, we're at a point where the slope of these two graphs is changing. So y1 is lower, it'd be at -5, so that's where it has a trough. And then y2 also has a trough at -4. 27 and a half, so we have 25, 26, 27 would be right here. So it looks like y1 is at about maybe -2.5 again. And then, sorry, y1's at -2.5, and y2 looks like it's at about 2. And then finally, at 30, this would actually extend just a little bit beyond what I've got here. So probably like somewhere like that. 30, then y1 is back to the x-axis, so it has no height. And then y2 would be at a crest, which is 4. Okay, now we want to form a superimposed wave. So to form a superimposed wave, we just add the amplitudes together. This involves using something called the principle of superposition. Okay, so y1 plus y2 would be 4. So there's a little bit of constructive, I don't know if I'd say constructive interference is occurring here because the height of y2 is not changing. Okay, here we're going to go 1.5 plus 3.25, so that would give me 4.75. Now, since the amplitude of both of these waves is increasing, there's a bit of constructive interference occurring there. At 7.5, 5 and -4 would give you +1. So there's some destructive interference occurring because you're getting closer to the rest position. At 13.5, 1.5, and 3.25 would give you 4.75 again. So again, there's a bit of constructive interference occurring here. Again, if your amplitude of one of your waves gets bigger, it's constructive interference. If it gets smaller, it's destructive interference. -2.5 at 2 would give you -0.5. -5 and -4 would give you -9. So I believe this is the area where you have maximum constructive interference. You're adding two troughs together to give you a huge jumbo trough. Then you have -2.5 and 2, which would give you pretty close to the rest position of -0.5. So these 2 points at 17 and a half and 27 and a half are like good points of destructive interference. And then finally at the end, 0 and 4 would just give you 4. So nothing really is happening there. Okay, now we're going to take y1 plus y2 and we're going to plot these points and try to form the shape of the graph. So when x equals 0, the superimposed wave is going to have a y value of 4. When x is 1.5, we're at 4.75. So 1, 2, 1.5, 4.75 would be about right there. Okay, and then we have at 7.5, we're at 5 and -4, which gives you 1. So 1 is going to be located here. Okay, and then at 13 and a half, we're up again to 4.75. So again, 13 and a half is about right here. We're going to go up to 4.75, which is located about there. And then the next point, 17 and a half, we're just a little bit below the x-axis. So here's 17.5. So we're at negative 0.5, which is going to be located here. And then we have a big dip down to negative 9 at 22.5. So going all the way down, negative 9. So we've dropped down here. And then we're back up to negative 0.5 at 27.5. So 27.5 is about right here. Negative 0.5. And then finally at the very end, we'd be at positive 4 again. Okay, so now what I need to do is I need to just draw a shape that's going to go through, that's continuous and goes through all of these little tiny points. Okay. Let's see how bad I can mess this up using a drawing tablet. Okay, so let's have a wave go here, then we'll have it dip down, then we'll have it go up, then we'll have it go down, then we'll have it go back up. You know what, that's pretty good. You have no idea how hard it was to actually draw that. So I deserve praise from that, but since I'm the only person here, I can just praise myself. Okay, let's go to example 2. A wave is incident on boundary A and reflects to boundary B. Calculate the angle of reflection from boundary B. This is ridiculously easy, as long as you understand a little bit about some interior angles with triangles. Okay, so I have an instant ray of light that approaches this boundary with an angle of incidence that's 50 degrees. So the angle of incidence be equal to the angle of reflection. Therefore, this wave ray hits, it's then going to reflect. I suspect I'm going to have a harder time with this, drawing a straight line than a curve. Yes, not looking so great. We don't need to take out a protractor and do this. We just need to make sure it hits the right surface correctly. Okay, so if that's 50 degrees, then this angle would also be 50 degrees, according to the law of reflection. Now, we can get this interior angle in the triangle because we know that the normal line is always perpendicular to the surface that the wave energy is reflecting off of, the wave ray reflects off of. So if that's 90 degrees, then this interior angle must be 40 degrees. Now, we have a triangle here that has an angle of 40, 110. And you should know that the sum of the interior angles in a triangle adds up to 180 degrees. So 40 plus 110 to be 40 plus 110 to be 150. Therefore, this missing angle here would need to be 30 degrees. Now, let's draw the normal line. So the normal line, again, is perpendicular to the surface at the point of contact. Ugh, that does not look good. Okay, so what do we know? Okay, so once again, the normal line is perpendicular to the reflecting surface. So if that's 30, then to add up to 90, this angle needs to be 60 degrees. And then we apply the law of reflection again. The angle of incidence is the angle of reflection. Therefore, the reflecting ray needs to bounce back at the same angle. So maybe something like this. And then this would be also 60 degrees. And it turns out that's the angle I'm looking for. It says, what's the angle of reflection from boundary B? Well, the angle of reflection is always measured relative to the normal line. So in this case here, it would be a 60-degree angle. Only the other thing I want to point out is when you draw these wave rays, you do need to actually have an arrow telling me what direction the wave energy is pointing. Like, you just don't want to draw a straight line, because a straight line isn't indicating direction, and a wave ray must indicate the direction of your wave energy. Okay, so that's it for this lesson, and you can complete the assignment called Interference in 2D Reflection. And then next time we'll get into a property of a wave that's referred to as refraction. Talk to you then.